out the notes and the relevant topics to be read in the textbook in the web page. Yeah, you can find the web page in the Teams general channel. Also, yeah, yesterday there was a office hours and very few people actually attended it. Okay, so either I am going very slow and yeah, things are too easy, or even the assignments are too easy. Yeah, in that case I would like to go a bit more faster. Okay.
Excuse me, sir.
Yeah.
Sir, actually today in the morning we had a deadline, so a lot of people yesterday were probably working on that, and even if they wanted to attend office hours, it might have been difficult for them. I just wanted you to take that into consideration.
Okay.
Yes, sir. I agree.
Yeah, so there is one more office hours on Thursday. I think Thursday afternoons is, at least in the timetable, it is marked completely free for you. Yeah. So one more office hours is there. So I'll be online in Teams. You can just ping me. If you don't find a meeting in the channel or anywhere else, you can just ping me and I will start a call with you. Okay. So yeah, so again these questions were coming again and again. So there was a question about, okay, where do you refer things, where do you solve more problems? So the textbook has been provided, and yeah, there are relevant chapters also has been given in the website. So you are expected to go over them. Yeah, there are a lot more exercises solved there. So if you are not clear with things, the best way to yeah, be clear about it is by looking at the textbook, reading it, solving more problems. Yeah. So is there any other questions regarding the course, about textbooks or where to find information and things like that? Okay, fine. So last time we asked the following question. Yeah, are all matrices diagonalizable? Yeah. So what do you think?
All matrices should not be diagonalizable.
Well, sir,
So
last class you already gave the answers no. So
yeah, so when is a matrix diagonalizable? Let's see if you recall that first.
If it is equivalent to a diagonal matrix.
Is equivalent to a diagonal matrix. So when is something equivalent to a diagonal matrix? What's the definition of equivalence?
So when there exists invertible matrix P such that M is equal to P M dash P inverse,
Okay.
then M and M dash are equivalent.
Yeah. And why do we diagonalize matrices? What's the purpose for diagonalization? Is there any particular reason we had to diagonalize matrices?
easy calculation.
It's easy to calculate. Okay, so easy to calculate. For example, transforming a vector with a matrix. Yeah, in general, it is n squared operations, right? And if you have a diagonal matrix, it's just the order of n operations. Yeah. Similarly, if you want to
square can be calculated easily, or the exponents of the matrix.
Yes.
In a diagonal.
Yeah. So if you want to do, yeah, it's much more easier to calculate the exponents when things are diagonal, right? If you want to do m raised to t and things like that. Okay. So so we told that the answer to this question is no. Yeah. So let's see a specific example. In fact, there is actually a very simple example. Can you diagonalize this matrix?
No, sir.
So why do you say no?
Its diagonal is already 0. Multiplying it by another matrix will not make the elements will not give diagonal elements, I believe.
So I think we can still swap the rows, right?
we can swap the rows.
Yes, sir, I think.
So if you swap the rows, you will get a diagonal matrix. So it is diagonalized.
Yes, sir, I think that.
So what is wrong with that argument? Does anybody want to?
We're using ordered bases, I believe, sir. So changing the rows is basically changing the order of the bases.
Yeah. So if you are doing something to the rows, you have to do the same thing to the columns also. Yeah. Remember, what do you mean by diagonalization? You have to do something like this operations. Yeah. So if you are doing something to the rows, you have to do the same thing to the columns also. Yeah, otherwise it's not diagonalization. So, okay, if you can permute the rows, but then you also have to permute the columns. Yeah.
So no matter what we multiply with, the bottom right element will always be 0. So it's not diagonalizable.
Okay. So yeah, fine. That is a good argument. That's a very simple and direct argument. Yeah. So yeah, another way to see it is what are the eigenvalues of this matrix? You can use your characteristic equation and find the eigenvalues. No.
Sir, 1 corresponding to identity matrix, I think, sir.
What is the eigenvalues of this matrix? Sorry.
0?
0.
0.
Is there any other eigenvalue?
No.
So 1.
No, sir.
1 is the eigenvalue of this matrix.
Yes, sir.
Why is that?
So you get lambda square is equal to 0. So it's only 0, right?
So, but if we pre-multiply by identity, we'll just get the matrix back, right, sir?
So
it's scaled
what
by
is the
1 only.
definition of a eigenvector eigenvalue? Sorry.
Sir, if the transform is M, then MV equals lambda V.
MV equal to lambda V. Okay. So which is the vector V you are talking about?
Oh, okay, sir. Sorry, sir. I misunderstood.
Yeah, sure. Okay, it's okay. I mean, yeah, it's good to ask questions. Yeah, and yeah, but yeah. So can the 0 vector be an eigenvector? The all zeros vector?
Eigenvector is defined to be not null, right?
Yeah. Eigenvector is defined to be a non-zero vector. Okay, remember that. But eigenvalue can be 0. Okay, an eigenvector is non-zero vector, but eigenvalues can be 0. Good. Okay. Now, so we are convinced that the only eigenvalue is 0. And what is the eigenvector?
So 1, 0 is an example.
Yeah, 1, 0. In fact, you can take any alpha 0, where alpha is not equal to 0. Yeah, and that's eigenvector. Yeah. And yeah, is there another linearly independent eigenvector you can find?
Sir, if it is linearly independent, then eigenvalue will change.
Yeah, I mean there's no other eigenvalue also, right?
Yes, sir, that's right.
There's no linearly independent eigenvector. Yeah. So basically, yeah. So this cannot be diagonalized. Okay. Yeah. So you can still ask the question. Okay, it cannot be diagonalized, but maybe you can convert the matrix into a very simple form. Okay. Maybe you can convert the matrix into a very simple form. Yeah. And apparently that is possible. Yeah. So if you remember the characteristic polynomial, yeah, so determinant of m minus lambda equal to 0. Yeah. So so this will factorize in the following way. So let's say lambda minus root 1 into lambda minus root 2 into lambda minus root 10 equal to 0. Yeah, let's say this is it's a real matrix and this is over the complex field. You can factorize this polynomial. Okay. So you will have n roots. Some of these roots might be the same. For example, R1 might be equal to R2, might be equal to R3, and R4 might be equal to R5, yeah, and so on. So yeah, so we will say the algebraic multiplicity of the eigenvalue R1 is equal to 3. Okay. So the algebraic multiplicity is the number of times that particular value is a root in the characteristic polynomial. Yes, this is called the algebraic multiplicity. Okay. And geometric multiplicity is basically equal to the dimension of the kernel of m minus lambda I. Yeah. So this is basically equal to the number of linearly independent eigenvectors with eigenvalue lambda. Okay. So this is called the geometric multiplicity of the eigenvalue lambda. Yeah. So yeah, so the algebraic multiplicity might not be equal to geometric multiplicity. Yeah, we saw one case in this particular case. Yeah, in fact, I mean the 0 has algebraic multiplicity 2, right? Do you agree?
Yes.
Yeah, 0 has algebraic multiplicity 2, and yeah, but geometric multiplicity is only 1. Okay. Yeah. So yeah, so this need not be equal.
Sir, how is it? How is the dimension of the kernel equal to the number of linearly independent eigenvectors? Like the kernel of m minus lambda I gives us contains all the eigenvectors corresponding to lambda.
Yes.
So the number of yeah, so that is fine, but I didn't understand how the number of linearly independent eigenvectors equal to the dimension.
So what is so kernel is also a subspace?
Yes, sir.
What is the dimension of a subspace? What do you mean by the dimension? It is the number of linearly independent eigenvectors, no?
Yeah, which span the subspace.
Yeah. So then this is equal to this.
Okay.
You agreed that every vector except the non-zero vector here, except the zero vector here is eigenvector. You agree with that?
Yes, sir.
Yeah. So the dimension of the subspace is going to be equal to the number of linearly independent eigenvectors with eigenvalue lambda.
Yeah, yes, I got it.
Yeah. Okay. Okay, so this is the case. Yeah. But even if this is the case, you can actually still simplify the matrix. Okay. So you can define what is called generalized eigenvectors. So this is some extra, information I am giving you. Yeah. If you are interested, I will give you a reference you can read up about. Yeah, so there is something called generalized eigenvectors, and there is always for every matrix, yeah, for every m, there are n. Generalized. So I haven't given you the definition of generalized eigenvector, yeah, but yeah, just I'm just giving you some information. And generalized eigenvectors, generalized linearly independent eigenvectors. Yeah, and using this, you can always convert any matrix. Suppose you have any matrix, yeah, you can always using a change of basis, that is P inverse MP. You can convert it to a matrix in the following form. Yeah. So in the diagonal matrix, only the diagonal entries are non-zero. Yeah. But here there will be some diagonal blocks. Yeah. In normal diagonal matrix, these blocks are 1 by 1 matrices. Yeah. But here it might be some matrix of dimension something else. and yeah, lambda 1 could be is there in the diagonal. Here it might be lambda 2. Here it will be lambda 3. Here it will be lambda 4. Yeah, and this entry will be equal to 0. Yeah, but this particular entry might be equal to 1. Yeah, so the off diagonal entries might be non-zero. Yeah, you might have a non-zero entry of 1 in the off diagonal. Yeah, and everything else will be 0. Yeah, and yeah, this is not exactly a diagonal matrix, but it's still easy to compute using this particular matrix. The number of operations is still not very high, right? Yeah.
So all these blocks have the same n cross n, right?
No. So this whole thing is n cross n. Yeah, and size of this block is going to be the algebraic multiplicity of lambda 1.
Okay.
Yeah, and yeah, it's not going to be exactly a diagonal matrix here, but there will be some off diagonal entries which will be 1. Yeah.
So all these blocks vary in size.
Yeah, they can vary in size. Different eigenvalues can have different algebraic multiplicities.
And they will be square, but that would
they will be square. Yeah, it will be a block diagonal. Yeah, it's a square matrix. Yeah.
Okay.
Yeah, and this particular form is called the Jordan form. Okay. So if you go through so there is a extra reading material given in the web page called Down with Determinants by Sheldon Axler. Yeah, so that explains more about this generalized eigenvectors and this particular Jordan form and everything. Yeah, so if you are interested, you can go through it. Okay, that's not really this won't come in exams or anything, but this is something very interesting to know. And yeah, if you go through the proofs, you will learn a lot. Okay.
So could you quickly brief up on what geometric multiplicity and algebraic multiplicity are? I'm not entirely sure about it.
So the algebraic multiplicity is number of times the eigenvector is a factor in the polynomial. Yeah, and if you sum up all the algebraic multiplicity, it will end up to be n, because any polynomial will completely become factorizes over the complex field, right?
Yes.
Yeah, but in fact, the geometric multiplicity of a eigenvalue is going to be less than or equal to the algebraic multiplicity. Yeah, so here we saw, there was algebraic multiplicity was 2, but geometric multiplicity was only 1 in this particular case.
Excuse me, sir.
Yeah.
So we'll never have a case where the characteristic polynomial has degree less than n. In that case, the algebraic multiplicities can't add up to n, right?
Degree, I think the algebra, it will be always be, yeah, so just a second. Yeah, but I think the polynomial degree will always be equal to n. Why is that? Because there will only be one term corresponding to lambda raised to n. There will always be a term corresponding to lambda raised to n, which will never get cancelled. Right?
So we can be sure of that.
Yeah. Lambda raised, how is the lambda raised to n going to get cancelled?
If there are imaginary roots.
When you do determinant of a minus lambda I,
Yes, so lambda will go in all the diagonals, right, sir?
Yeah. So that lambda raised to n, how can it get cancelled?
Sir, if there are imaginary roots.
But I don't think that will affect the degree of the polynomial, whether or not there are imaginary roots.
Yeah. So what I was saying is, if you expand the determinant, the lambda raised to n term will never get cancelled. Yeah. So the degree of the polynomial will always be equal to n. So it will have n roots. Yeah. So many of the roots might be repeated. Some of the roots might be equal to 0. All those things can happen.
Okay, sir.
Sir, what if there is lambda square plus 1?
Yeah, it will be lambda minus 1 into lambda squared plus 1 equal to 0. So it will be lambda minus I into lambda plus I.
So how can we?
So it's a complex root.
Okay. I mean, if mv is equal to I into v, but all are real entries, that's not possible, right, sir?
Yeah. So I mean, this fact that a polynomial factorizes into this kind of factors is only true over complex numbers, right? Yeah. So what you are saying is a real matrix, yeah, can have complex eigenvalues. That's what you are saying.
Yes, sir.
Yeah. So yeah, I mean, all this is true when you have a real matrix and you are talking about eigenvalues also over the complex this thing. Yeah. And typically that's how people think about it. Yeah. So if we are only restricting to real root, then then all this doesn't make sense.
But eigenvalues are defined like vectors which satisfy mv equal to lambda v. So the matrix entries also can be imaginary in that case.
No, the m will be real. So you are given this matrix m which has real entries, but your eigenvector and eigenvalue can be complex.
Okay.
Yeah, and then mv equal to lambda times v, where lambda as well as v are complex numbers. Yeah, for example, let's look at example. For example, your rotation matrices. Yeah, I think if you take this rotation matrices, they have complex eigenvalues. Yeah, they don't have a real eigenvalue. Let's say you have a matrix which is there is this cos theta sin theta matrix, no, that you guys know. Yeah, if you want to rotate a vector by angle theta, you will use this cos theta sin theta, some matrix like that. And that matrix, if you compute the eigenvalues, it happens to be complex numbers. I will give a particular example in the next lecture or in the assignment. Okay. Yeah, so let's move on to the next topic in the course. Okay. So the next topic we want to cover is norms and inner products. Yeah. So you are already familiar with some level you understand what norms and inner products are. So what is the norm of a vector? Norm of a vector is the length of the vector, right? Yeah, so how do you define the norm of a vector?
So square root of its inner product with itself.
Okay. Square root of the dot product with itself, you are saying?
Yes, sir. So inner product in general, sir, I think.
Yeah,
So
inner product in general.
So I remember from the internal sales class, it was defined using inner product.
Okay, I see. So he already covered some amount of inner product. Okay, good. So I will just recall those definitions. Yeah, in the next lecture, we will basically use these definitions more. We will see more examples. Yeah. So this is called the norm of a vector. This is the length of the vector. Yeah. The thing is, in this course, we will be looking at more general norms. Okay. So in your schoolings, you worked with the vector spaces, which was basically tuples of real numbers. So these kind of vector spaces, R raised to n, is called Euclidean vector spaces. Okay. Yeah, this is a real Euclidean vector space. Yeah, but in this course and many of your future courses, you will be looking at vector spaces which are not Euclidean. Yeah, where the definition of length of a vector is very different from this. Yeah, where the dot product is very different from your usual dot product. Yeah. So we need to think of norm not in terms of this always. Yeah. For example, a very common norm that is used is what is called the pth norm. Yeah. So the pth norm is obtained by you take the modulus of v1, yeah, and absolute value, raise it to the power p and sum it up. Yeah, and take the 1 by p of this. Yeah. So your normal norm is basically the 2th norm. Yeah. But in your future courses, you will see pth norms also. Okay, and especially when you have probability distribution and all, for some reason the 1th norm is basically better to use. So what is the 1th norm? 1th norm is just taking the absolute value of v1 plus absolute value of v2 up to absolute value of vn. Yeah, this is basically the 1th norm. Okay. Yeah. There's also something called the 0th norm. So what is the 0th norm?
N.
It's not always n, it is the number of non-zero entries in the vector v. So if v1 equal to 0, that particular entry, I mean, this thing is going to be 0.
But 1 by 0, sir.
So you are right. Yeah, 1 by 0 it becomes a problem. Yeah, you are right. Yeah, but v0, I mean, I think it is defined as the number of non-zero entries in the vector. Yeah, so yeah, I agree. There is a problem with this general formula, but yeah, v0 is defined as the number of non-zero entries in v. Okay.
So here v is column vector v1, v2 till vn.
Yes, v is a column vector v1, v2 till vn. In this course, if I write v1 to vn, typically it will be a entries of the vector v of the column form. Okay. Yeah. Some of the textbook they like to write vectors as raw vectors. Yeah. Yeah, it's always a big debate. Some people like column vectors, some people like raw vectors. Yeah, I was taught with respect to column vectors, so I'm going with that. In my, during my research work, I was taught with respect to column vectors. Okay. Yeah, similarly, if you have a matrix M, Mij, yeah, is the ith row, jth column entry. So these are commonly used. Yeah, Mij, the ith row, jth column entry is Mij. Similarly, if you have a vector v, v1 is the first entry, v2 is the second entry, and so on. Okay. So okay, now we understand what you mean by length of a vector. So what are the conditions? Suppose I want to define the length of the vector. Yeah. So in general, yeah, it is a function. A norm is a function, yeah, which maps the vector space to a positive real number. Norm is a function which maps the vector space to a positive real number, and it satisfies the following conditions. Yeah. So what are the things that you expect a length to satisfy?
So non-negative real number. Okay,
yeah, I already said it's r plus, so yeah, but yeah, you are right. So the norm of a vector is going to be greater or equal to 0 for all vector belonging to the vector space. Yeah, and when can it be equal to 0?
For the 0 vector itself.
Yeah, it is equal to 0 if and only if v is the 0 vector. Only for the 0 vector it can be equal to 0. Every other vector has a greater than 0 norm. Okay.
Sir, one question. Sir, the notion of length is being associated only to the 2th norm, right?
No, So no, that is if you are looking at Euclidean spaces, and in your courses you will look at you will redefine length to be something else. This might be your definition of length. Yeah, and we won't be using the word length. We'll be using the word norm.
But we are drawing an analogy though, aren't we?
Yeah, we are drawing an analogy. Yeah. So yeah, you can say that this is the length. Yeah, and norm is more the abstract notion of length.
Understood. Thank you.
Yeah. And also length also satisfies some other inequalities, right? Which you also learned in school. Yeah, so if you have two vectors v and w, yeah, so some other inequalities are also satisfied by the length of a vector. What is that?
Triangle inequality.
Triangle inequality. So what is triangle inequality?
Is greater than equal to v minus w.
Less than equal to that, sir.
Yeah. So yeah, there's multiple ways to write it, but I think if you just write this, the other thing also follows, I believe. Yeah. So I think you just need to write this, and the other thing also follows, I believe. Yeah, and yeah, as you said, this is also less than equal to norm v minus norm w. Okay. Yeah. Yeah. So yeah, if you have these three conditions, then you have a norm. Okay. So yeah, what else have you learned about normal vector spaces that we haven't covered?
So I think norm is this much only, sir. There's some stuff about inner products and its bilinearity.
Yeah, that's right. So there's also something called the distance of distance notion, no? Distance between vectors.
Yes, sir. U minus w.
Yeah. Yeah. So how do you measure the distance between a vector v and w? Yeah.
Inner product of v minus w.
Yeah, it is the norm of v minus w. Right?
Yeah, sir.
So that's how you measure distance between vectors. Fine. Then there is so also normal vector spaces have this notion of angle and projections and everything, right? Yeah. So what is the notion of angle, projections, and everything?
So do all vector spaces do that?
Yeah. So do all vector spaces do that? Yeah. So remember, whenever you have norm, you already said real numbers here. Where is this? Where did I define? Okay, that went here. Sorry. Let me just. Yeah. So vector spaces generally also have something called angled projections and everything. I mean, your real vector space that you taught in schools had this concept of angle and projections. Yeah. So yeah, so if you have a vector v and you have another vector w, yeah. So what is the projection of w onto v? Yeah. So what is this length?
Sir, the mod w cos theta.
Mod w cos theta. Okay. So we don't want to introduce the concept of angles here. Yeah.
W bar.
Yeah. Instead, we will bring in the concept of angles through the concept of dot products. Yeah. So basically, it is w dot v. That's enough.
Into v cap.
Yeah. You also need to divide by something, no?
Divide by
Okay.
Not V1.
Yeah. So we need to divide by the norm of V. Okay. Yeah. So this is the projection of a vector W onto a vector V, right? Yeah. So yeah. So you
means the length or the vector.
The length. Yeah. I'm saying this particular length is this. Is that right?
Here, dot refers to the inner product, right?
Yes.
Yeah, dot product refers to inner product. Yeah. We are referring to the dot product. So dot product between a vector and another vector is summation over I equal to 1 to n wi into vi. Okay. Yeah. So yeah. So this
Also,
this
can we say that lambda time norm of lambda times v is the same as lambda times norm of v? Is that like a possible statement? Like it gets scaled by?
Yeah, so we haven't written down here in this general in this conditions. That's what you're saying. Yeah? So maybe
so,
that condition is also needed. That's right. Yeah.
But the thing is, like, wouldn't the zeroth norm not satisfy that? Because if I multiply it by lambda, the zeroth norm still remains the same, right? So will it be treated differently?
Yeah, that is right. Maybe the zeroth norm is actually not a norm. Okay. Yeah, so this particular thing might not be actually be a norm. So, but this definition exists. You might see this definition at various places. Okay, so just remember that typically V0 is basically the number of non-zero entries. Yeah, but this might not be a norm. Okay. Yeah. Thanks for pointing that out.
So that means we are considering 0 raised to 0 as tending to 0.
So it is just a definition. Okay, so it might not mean anything general. Okay, so you can just ignore this comment. Possibly this is possibly some special notation rather than something very generic.
Okay.
Okay, so we have the concept of dot product, but this is for real vector spaces. Okay. So what is the concept of dot product for complex vector spaces? Do you know that? Yeah. It is very similar, except you have to take a conjugate also. Yeah, so Vi might be a complex number, so you might need to take the conjugate also. Yeah. So yeah. So in general, our dot product might not look like this. Yeah. So in general, yeah. So a dot product, an inner product is a function. Yeah. Inner product is a function. So we might represent the inner product like this. Yeah. It maps a pair of vectors. Yeah. To a real or complex number. It's a real vector space, you will get a real number. It's a complex vector space, you will get a complex number. Okay. Yeah. And it satisfies the following properties. Yeah. So the inner product of a vector with itself has to be greater or equal to 0 for all vectors. Yeah. And the inner product of a vector with itself is equal to 0 if and only if v equal to 0. Okay. And you can add something in the first coordinate, and then it is linear in the first coordinate. So this is linear in the first coordinate, and finally so you can also do scalar multiplication in the first the first part. So it will become just And
Sir?
yes.
The earlier definition, we were given that inner product space maps to positive real non-negative real numbers.
Yeah, that is the norm, not the inner product.
No, sir, I mean in the earlier part of this course.
Not necessarily. It can also map to complex numbers. Yeah. Inner product can also give you a complex number if I understand correctly. Yeah, inner product can also give you a complex number.
Sir,
Just
I
a
ask it
second.
out?
Just a second. Just a second. Yeah, I think inner product can also give a complex number as output. There's nothing wrong with that.
Sir had mentioned while teaching us that he is only considering real numbers for a reason, as in complex exists, but he will only be dealing with real numbers for the course.
Yeah, yeah,
so that's
but
why that's what he said.
Yeah, yeah, that's what he said. Yeah, yeah, but later if you take internals courses, he will also be dealing with the complex vector spaces. If you take his elective courses in the next semester and everything, he will teach you quantum computing and everything, and where there will be a lot of complex vector spaces coming up. Okay. So,
sir,
yeah,
we took the conjugate in complex spaces in order to produce a real number output. I don't understand that part, sir.
So only I'm saying is a inner product can also give you a complex number
Sir,
as output.
above that, sir, above that, in the dot product for complex numbers, why did we take the conjugate?
So that is the definition. So if you only do this, then these conditions are satisfied.
Which condition, if it's not a conjugate, which condition is not satisfied? So could you just?
Yeah. So I haven't finished the conditions. Yeah. Before that I was stopped. Okay. So let me just add the final condition also. So there is a condition which says this. Yeah. So the inner product of V to W, it's not exactly symmetric. This is called conjugate symmetry. Yeah. If you just flip it, then you need to take the conjugate also. Yeah. And if this has to be satisfied, then you better define dot product like this. You agree?
Okay, so this condition was not. It was done a bit differently. It was they took a derived case of this for real numbers in internal search class. Now
Okay.
it would make sense, sir. Thank you, sir.
Yeah, sure. Yeah. Yeah, it's a very, I mean, this is a very unnatural thing, especially these complex numbers are very unnatural. It's very difficult to physically motivate it. Yeah. But apparently this also happens in real world. Like whenever you deal with this quantum systems, yeah, somehow there also this laws of physics work with this quantum laws. Yeah. I mean, you can have a cat sitting in a box where yeah, I don't know, some radioactivity is there, and the cat can be in alive as well as a linear combination of alive as well as dead states. Okay. Yeah, it's very difficult to intuitively imagine initially. Yeah, but in many situations, especially in quantum computing and everything, you will have situations when things can be only be described by these laws, these rules of vector spaces. Okay.
So here in W dot V, is W also complex or just V is the complex in the left page?
So V is a complex vector space.
So no, on the left side of the page is V1. You only took the complement of Vi, where we have defined dot product. Yeah, the second one.
Yeah.
So we are only taking the conjugate of Vi. So
yeah, of the second part of the vector on the right side of the dot product, we are taking the conjugate. Yeah.
Okay, so W can also have complex values, right?
Yeah, so V and W are from a complex vector space, so they can have complex values.
So, but we are taking only of the second vector,
yes,
the conjugate.
Yes.
Okay.
Yeah. So this particular definition is required for satisfying this conjugate symmetry.
Yes.
Yeah. If you are defining an inner product should satisfy all these conditions, and if you simply define the normal dot product, then this conjugate symmetry is not satisfied if your vector has complex entries. Yeah. And yeah, this particular definition of dot product makes sure that the conjugate symmetry is satisfied.
So for real numbers, it won't be conjugate. For real vector spaces.
Yeah, real vector spaces, conjugate is the same number itself, so no problem.
Okay.
Okay. So yeah. So given an inner product, can you define a norm based on an inner product?
Mod of inner product.
Yeah. Norm of a vector, if you define it as the yeah. So we already said, so this is always a real number, no? In fact, this is always a positive real number. Why is that?
Unless p is 0, it will always be a positive.
Sum of squares.
Yeah, yeah, that's right. So yeah, so this particular thing is called So given an inner product, you can define a norm based on this. Okay. So our inner product might not always be the dot product. It might be some other thing also. Yeah. In which case, the norm will be defined like this. Yeah. So some of you, especially the electronics people, will have the signals and systems course later, and there you will be considering different definitions of inner product. Okay, in terms of expectations and everything. And the norm happens to be the energy of the signal or something like that. It will work out to be.
Sir, if V is a complex number, then how is the inner product of V to V is a real number?
So if I do inner product of V with itself, yeah. Yeah. So it's already written here. For all inner product of V with itself has to be a positive number.
But sir, it can be complex number also, no? If V is complex.
So you are saying with the normal definition of dot product.
Yeah,
yeah. So if I substitute Wi to be equal to Vi, what happens? If you substitute Wi equal to Vi
okay,
here.
Sir, okay, sir. Okay, I got that, sir.
Yeah. That's why this definition was needed for complex vector spaces. Okay. Yeah. So now you understand why I had to redefine dot product for complex vector spaces, right? Okay. Okay. So yeah, let's just recall what we did today. Yeah. So yeah, we just saw that okay, there is this particular matrix. In fact, there are many matrices which cannot be diagonalized. Yeah. And we had some discussion about it. Yeah, we defined what is called algebraic multiplicity and geometric multiplicity. Yeah, and we said that we didn't prove all these things, but if you go through this particular reading material given in the, in the website, yeah, you can read more about it. Yeah.
Sir.
Yeah.
In the matrix example for the diagonalizability, we calculated the eigenvalue and the eigenvectors, and since there is only one eigenvector, we are saying it's not diagonalizable, right?
Yeah, there is only one. You cannot find a second linearly independent eigenvector. Yeah.
Okay, that's why we are saying that it's not diagonalizable.
Yes. So if it is diagonalizable, you have to find a basis of eigenvectors which are linearly independent. So there should be two eigenvectors which are linearly independent if it has to be diagonalizable.
Yes, sir.
Okay. So yeah. So yeah, so we said that okay, any matrix may not be converted into a diagonal matrix, but it can be converted into a matrix with diagonal as well as off diagonal entries. Yeah. And this matrix is also reasonably simple. Yeah, if you want to do powers or if you want to do vector multiplication and everything, this particular matrix is also reasonably simple. Yeah. So yeah, in case you have a non-diagonalizable matrix, you might want to do this. You convert into a Jordan form. Okay. Then we went into some definitions, okay, of some normal things that you have learned. Just that we will be defining some conditions. For example, norm, this is the usual definition that you learned about for Euclidean vector spaces. Yeah, but we will be considering general norms, yeah, which satisfy these conditions. Yeah. For example, one example of this is basically this particular norm. This is called the pth norm. Yeah, so this is called the pth norm, or it's called the LP norm. Yeah. So the normal norm that you do is called the L2 norm. And
Sir,
yeah.
I have a doubt.
Yes.
Sir, in the expression of norm, what does V1, V2 up to Vn represent?
They are the coordinates of the vector with respect to the standard basis, current basis.
Okay, yeah, thank you very much.
Yeah, yeah, so similarly Mij is the entry in the ith row, jth column of a matrix. Yeah, so yeah, okay. Yeah, so once we define a norm, we can also define what is called distance between vectors, yeah, which is basically the norm of the difference of the vectors. And we can also define angles and projections. Yeah, for defining angles and projections, we need something called an inner product, and inner product is a generalization of your usual dot product. Yeah, one thing, when you generalize dot product to complex vector spaces, you also need to consider this conjugate on the second vector. So something to be known. And a inner product is a generalization of a dot product. It has to satisfy these conditions. Yeah, and it has to have this conjugate symmetry also. And you can also define a norm based on the inner product by this definition. Okay. So yeah, these are just some definitions. In the next lecture, we will be seeing more examples. We will be seeing more uses of this. Yeah, and in fact, for some special matrices, you can. So this earlier theorem of diagonalizability will be generalized, and there will be very special eigenvectors. Yeah, which are not just just simple bases, but also some special type of basis which allows you to compute it much more faster. Okay, so and we will look at what is called spectral theorem and everything later in the course, which requires this kind of inner products and everything to explain.
So can we always convert any matrix to the Jordan form?
Yeah, you can always convert any matrix to the Jordan form. That is, it will have diagonal entries as well as off diagonal entries by means of this kind of a transformation.
So off diagonal entries means the entries will be non-zero in the smaller matrices, right? The blocks.
Yeah, in the blocks. So this is the diagonal. Off diagonal is the diagonal entries just next to it. Yeah, and in fact you can make all of them one also. You don't. They need to be arbitrary numbers. In Jordan form, you can make them one also.
You mean the off diagonal entries?
Yes.
Because it means that there are only 3 diagonals of entries in the Jordan form.
So actually, you only need 2 diagonals. You can make the other diagonal 0 also.
Excuse me, sir. Sir, in the first part, sir, I understood everything until geometric multiplicity. Sir, I didn't understand how from that we said that the matrix is not diagonalizable.
So you don't understand this, why this matrix is not diagonalizable?
Yes, sir. I didn't understand how we got the implication.
Okay. So what are the eigenvalues of this matrix?
It's a 0.
It has only the 0 eigenvalue. You agree?
Yes, sir.
Yeah. What is the eigenvector corresponding to 0?
Sir, alpha 0, sir.
Alpha 0. Can you find a linearly independent eigenvector from this?
No, sir.
Why? Why can't you find? How can you say there is no linearly independent eigenvector other than alpha comma 0?
So because there's only one other eigenvalue, right? So and so they'll also have the same eigenvector, and if we can always scale one of these to another alpha 0.
So you are saying there cannot be linearly independent eigenvectors with the same eigenvalue. Is that what you are saying?
So I'm not sure.
So why can't we find another linearly independent eigenvector? Yeah. So take a linearly independent eigenvector from this. Yeah. So either it will have both the entries non-zero, or it has a second entry non-zero only, right?
So if it exists, yes, sir.
Yeah. But you can easily show that both the types of those vectors are not eigenvectors.
Yes, sir.
Yeah. So the only type of eigenvectors is of this form.
Yes, sir.
Yeah, and all of them are linearly dependent.
Yes, sir.
Yeah. So there is, you cannot find two linearly independent eigenvectors.
Okay, sir.
So end of proof.
So how does that directly imply that it's not diagonalizable? Sorry, sir.
So a matrix is diagonal. When do you say a matrix is diagonalizable?
So when it's equivalent to a diagonal matrix.
It is equivalent to a diagonal matrix. Yeah. So what is this P? The P is changing from your current basis to a basis of eigenvectors.
Yes, so basis of eigenvectors.
Yeah. So if you have a basis of eigenvectors, it is diagonalizable. If you don't, it is not diagonalizable.
Ah, okay, sir. Okay, I understand. So if both our eigenvectors are the same, then it will never be diagonal that way. Yes, sir.
Yeah. Yeah. So if and only if. Yeah. Works both ways.
Okay, sir. Thank you, sir.
Yeah.
So in general, how can we say if a matrix is diagonalizable or not?
How can we say if a matrix is diagonalizable or not? Yeah, you will need to compute the algebraic multiplicity and geometric multiplicity and see if they are equal. So it's easy to compute the algebraic multiplicity and geometric multiplicity, no? So you just need to look at, the characteristic polynomial and look at the roots. The number of roots with the same value is the algebraic multiplicity. You can also look at the kernel of dimension of kernel of m minus lambda I. That will give you the geometric multiplicity. If geometric multiplicity is strictly less than algebraic multiplicity for some eigenvalue, then it's not diagonalizable. Is that?
So for all the eigenvalues, we should have algebraic equals to geometric.
Yeah, then only it's diagonalizable. Yeah.
Oh.
So I don't understand how we are linking geometric and algebraic multiplicity to diagonalizability.
Yeah. So if you sum up the algebraic multiplicity, what are you getting?
The number of linearly independent rows or columns.
No. If you sum up the algebraic multiplicity overall,
actually, you're getting the order of the matrix.
You will get n basically, right?
Yes, sir.
Because this is a polynomial over a complex polynomial. It will has n roots. Yeah, and this is a degree n polynomial. The nth degree n term is not getting cancelled out. Yeah, so it will have exactly n roots. Yeah, so if you look at the sum of algebraic multiplicity, it has to be exactly be equal to n. Yeah, now suppose the geometric multiplicity is equal to algebraic multiplicity for all the eigenvalues. Yeah, then you have a basis of eigenvectors, right? Why is that?
The basis of which subspace?
Of the entire vector space. Basis of eigenvectors for the entire vector space.
Yes, sir, because we are getting n linearly independent eigenvectors with eigenvalue lambda.
Yeah, why is that? Is that clear? It's there's one or two steps involved actually to make that conclusion. So for every eigenvalue, yeah, you will have basically algebraic multiplicity number of linearly independent eigenvectors, right?
Yes, sir.
Yeah, and also eigenvectors corresponding to different eigenvalues are linearly independent.
Yes.
Yeah, so now you have n linearly independent vectors which are also eigenvectors. Yeah, and that means it is diagonalizable.
Sir, how n linearly independent vectors? Because this.
So if geometric multiplicity equal to algebraic multiplicity, yeah, then the dimension of the kernel of this matrix is equal to basically that algebraic multiplicity, right?
Oh, if equal to. Okay, I missed that part, sir. Okay.
Okay, I think it's already over time. Yeah, so I mean I'll be already taking questions now.
So could you scroll right a bit?
Sure.
So yes, sir. Here, how is the conjugate of a general vector? How are we?
So this is only for complex vector space. Okay, so this definition is only for complex vector space. So Vi is a complex number that is assumed here. Is that fine?
So, but that why? So why are we taking conjugate?
Sorry,
Why are we taking?
So that is the definition. Because suppose you want to define norm, yeah, based on the dot product, yeah, norm is the square root of the dot product, right?
So that is not the dot product.
Sorry.
So that is not the dot product, is it? Because dot product we don't take conjugate.
A dot product is a inner product. Inner product is a generalization of a dot product. So a dot product is also an inner product.
Yes, sir. But this definition with the conjugate is not the dot product, is it?
So this is the definition of dot product in complex vector spaces. If your vector space is a complex vector space, then you need to define dot product like this. Otherwise, you will not be able to take norms.
Oh, okay, sir. Got it, sir. Thank you.
Because otherwise, you will get a complex number here. Yeah. Okay. If there are no other questions, we can close the meeting. Okay, then thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you. Bye.